So I welcome you all, dear students. In today's class, we will continue with our discussion on amplitude modulation. In the yesterday's class, we had firstly talked about the concept of modulation, and then we finished our class with concluding remarks on amplitude modulation. And we had seen what is amplitude modulation. We had also derived the expression for amplitude modulation. We had seen the time domain representation and the frequency domain representation of amplitude modulation. So in line with that, we will continue with our discussion on amplitude modulation. And I hope all of you will be able to understand further concepts of amplitude modulation. Okay. So these are the books that we have already talked about. So in this slide, I'm just briefly touching upon what we discussed with regard to the expression of amplitude modulation. And I told you in the previous class that in amplitude modulation, the amplitude of the carrier is varied in accordance with instantaneous value of modulating signal. Yesterday, with the help of mathematical expression, we had clarified our concept related to instantaneous value and related to amplitude of the carrier signal. Okay, and then we had derived the expression for amplitude modulated wave, and this was the expression that we had derived, which gives us the instantaneous value of the amplitude modulated wave. And with the help of this expression only, we are able to obtain this waveform of amplitude modulation. And I had clarified that in this expression on amplitude modulated wave, VC is the, in fact, VC into 1 plus m sine omega mt. This is the amplitude envelope of the instantaneous value of the amplitude of AM signal, and the carrier frequency remains same in AM, that is your omega c. And by applying the trigonometry entities or the properties, we can further solve this expression, and we get this expression, that is VAM equal to VC sine omega CT, then plus of MVC by 2 cosine of omega c minus omega m into t, and minus of MVC by 2 cos omega c plus omega. So this is nothing but the same expression as the above one, but by looking at this expression, we are able to find out that in the expression of amplitude modulation, we have three frequencies present. One is carrier frequency, another is this lower sideband, another is your upper side. Okay, and M I had talked about, M is equal to Vm by Vc. Next. So as I told you in the previous slide, that we have assumed M equal to Vm by Vc, and this M is very, very important parameter with respect to amplitude modulation. And I didn't talk about its name in the previous class purposely. So now I tell you what is M. M is called modulation index. Okay, so this is what we are talking about in the next slide. This slide is dedicated to modulation index. And what is the meaning of modulation index? Modulation index tells us about the percentage of modulation. Okay, so students, if you remember, I told you that what happens in modulation. In modulation, we superimpose our information signal or modulating signal onto our carrier. Okay, so you can see this, that this is our information signal and this is our carrier. Okay, so it is the information signal which is giving us the modulation onto the carrier. So this modulation index tells us that how much percentage of modulation has taken place. Okay, so and this is measured in terms of this parameter M, which is equal to Vm by Vc. Vm is the amplitude of modulating signal, and Vc is the amplitude of the carrier signal. And see, ideally or practically, the value of modulation index lies between 0 and 1. So it is greater than 0 and less than 1. I'm sorry, I have used the wrong sign here. It should be the reverse way. It should be m should be less than 1 and m should be greater than 0. It should be like this, that m should be greater than 0 and it is less than 1. So this, the value of modulation index lies between 0 and 1. So if you again look at this definition of modulation index, where Vm is it is equal to Vm by Vc, when we say that m should be less than 1, that means that your amplitude of modulating signal, it should be less than the amplitude of the carrier. Okay, so for practical purposes, the amplitude of modulating signal has to be less than carrier. Okay, so that means that here this amplitude of the modulating signal, it cannot be more than the amplitude of the carrier, and that is understandable also because the purpose of carrier is to carry information signal. So how can we carry something which is bigger than the carrier? So your information signal or modulating signal cannot be larger than your carrier. Okay, so now if you look at this figure carefully, we need to derive or express our modulating signal in terms of some other parameters. From there we get that this Vm is equal to Vmax minus Vmin by 2. And how do we get that? So you look at this figure carefully. What is Vmax? Vmax is the maximum value of the modulated signal from 0. Okay, so from 0 line to the top peak, this is Vmax. Okay, and what is Vmin? Vmin is the minimum value of the envelope, that is from 0 line to the minimum possible value of the envelope. Okay, so this is Vmin, and like if you subtract Vmin from Vmax, we are left with this portion. This portion means this much value. And how much is this value? This value is twice of Vm. Okay, so we want Vm, so that's why this Vm is equal to Vmax minus Vmin by 2. So just by simple observation, we will be able to get this. Similarly, now we need to find out the value of Vc. Now, what is Vc? If you look at the graph carefully, this is Vc. Okay, and how do we get this value? So from the 0 line to the maximum value of the amplitude, this is Vmax. So from Vmax, if we subtract this Vm, okay, so what we do, Vmax minus amplitude of modulated Vm, and then we substitute this value of Vm here. Okay, so we get Vc is equal to Vmax plus Vmin by 2. So if you divide the two, you get the modulation index formula as Vmax minus Vmin by Vmax plus V. So these both you can say expressions are important, though the primary expression, that is your modulation index equal to Vm by Vc, this is your primary formula that you have to memorize, and this is another formula which tells us the maximum value of the envelope and the minimum value of that. Okay, so this is our modulation index, which tells us, so what is the significance of modulation index? It tells us that how much percentage of modulation has taken place. So obviously the percentage of modulation can be from 0% to 100%. So that's why the value of modulation index lies between 0 to 1. Fine. Next. So students, since we are talking about the value of modulation index between 0 to 1, so now what happens if the modulation index value is more than 1? Okay, so m is greater than 1. In that case, we call that thing as over modulation. Okay, so when your modulation is greater than 100%, we call it as over modulation, and this over modulation is never desirable. And why is it so? Because this over modulation leads to distortion of the signal. See, the purpose of modulation is to transmit the exact signal from one place to another place. Okay, that is the purpose of carrier. And if because of our modulation our signal distorts, then there is no point in having that modulation. So here, if we look at these figures carefully, first you look at this figure, figure number 1, which I have taken. So here, my modulation index value is 0.5, means 50% modulation is being done here. Okay, m equal to 0.5 means your Vm is half of Vc. So if you see here that this is your V max and this is your V min. Fine, and it is 50% of that. Okay, so it is the actual AM signal that we have proposed here. Okay, now you look at this thing carefully. What happens if I increase the amplitude of the modulating signal without changing the amplitude of carrier? So then what will happen? This signal will look like this now. Then if you increase the amplitude of the modulating signal. Okay, so what is happening? So similarly, this will increase at the downside also. So it becomes like this. Correct? So what is happening as you increase the value of amplitude of modulating signal? Okay, if you increase this, then what is happening? This Vmax values, the gap between Vmax values, it is increasing, and the gap between Vmin values, it is decreasing. Okay, those Vmin values, they are coming closer. Okay, let me redraw it. See this portion. If you increase the value of Vm, these things will come closer. Okay, closer to zero line. Okay, and when your Vm equal to Vc, when Vm equal to Vc, then both these bottom peaks, they will merge with each other like this. So here 100% modulation has taken place. Okay, in this case, the value of m equal to 1. So your negative peaks, they touch each other, just touch. And if you see, just touch each other means there is no carrier at this instance of time. So that's why we say that the value of modulation index lies between 0 and 1. And what happens if you further increase the value of modulating signal amplitude, then your m becomes greater than 1. Then what will happen? This positive negative side of you can say positive signal, it will come downwards and they will cross each other. I'll redraw just a minute. They will cross each other. So this will come downwards like this, and this lower signal will come and cross it. Okay. So when it crosses it, then what happens? Then your negative part, it has moved into the positive part, and the positive portion, it has come into negative. Means there is reversal of the values. Okay, and that has been shown here in the figure number 3. So when your modulation index becomes greater than 1, that means your Vm becomes greater than Vc. In that case, your peaks takes the reverse values, they cross each other like this. Okay, the positive portion has come in the negative, and the negative portion has come into the positive. Okay, and because of changing the sign, then what is happening? The carrier inside this envelope, the carrier exhibits phase reversal. Okay, means whatever signal was supposed to be going in positive direction, it is moving to negative, and negative is going to positive. So that means because of over-modulation, your phase reversal takes place, phase reversal of the carrier values. Okay, and because of this phase reversal of the carrier, signal is distorted. That's why your modulation index, in case of amplitude modulation, it can never be greater than 1 because it leads to distortion due to phase reversal. And I hope all of you have understood the concept of phase reversal. Fine. That was about your modulation index. One more thing I have pointed out here in this slide, that is your trapezoid method. Okay, see students, you will also be performing experiments related to amplitude modulation in your analog and digital communication lab. So in the previous slide, we saw two expressions of modulation index. One is Vm by Vc and another is Vmax minus Vmin divided by Vmax plus V. So this formula of Vmax minus Vmin divided by Vmax plus Vmin is important when we want to obtain the value of modulation index in the lab. Okay, so in the lab, when we use CRO with our amplitude modulation kit, then with the help of CRO, we can measure the modulation index value directly. And that method is known as trapezoid method. Trapezoid method. Okay, so I'm not going to explain this method here in the class. I will suggest you people to once go through this trapezoid method, and then we will discuss this method in the lab detail. Just to briefly tell you that when you try to measure modulation index in the lab using CRO, then you come across such kind of waveform on your CRO, and the larger side of this trapezoid, it is called Vmax, and this smaller side of trapezoid called Vmin. So you can directly measure Vmax and Vmin, and then by applying the formula, you can obtain the value of modulation. So that way, the concept of modulation is very, very important, and you can measure it directly. So I hope this thing is clear to everyone. Now let us move forward. So once we have now talked about the concept of modulation index, and we have also seen the expression of AM signal. Now, see, this was the AM signal that we had talked about. And I told you in the previous class as well, that in the AM signal, we have three things present. One is the carrier. Another is your lower sideband. Okay. And third thing that we have observed here is upper side, which I explained in the last class. Upper side. Okay, so now if we want to obtain the power of your AM signal, okay, so want to obtain total power of AM signal. So obviously the total power of AM signal will be the sum of the power of its individual components. Okay, so in AM signal, we have three components. One is the carrier part, then the upper sideband part, and then the lower sideband part. Okay, and we know that how do we obtain power? The power of any, say, if we have a sine wave, which is represented by expression, say, A sine omega CT. Okay, and if I ask you that how much is the power of this sinusoidal signal, then obviously if we want to obtain power, then power is equal to the root mean square voltage, okay, RMS value of the voltage divided by R. We know that power is equal to V square by R. We know that this is the power relation. And what is this V? V is the root mean square voltage value, RMS value. You already know that. Okay. So now since we have three components, so we will take the RMS voltage value of these three components. Okay, we will square that, divide by the resistance, and then we get the total power. So first let us take the power of carrier component. So this is the power of carrier component, V square by R, where this V car square is the RMS value of the carrier. Okay, then this is the power of lower sideband component. This is the power of upper sideband component. So these are the three components, and if we sum them together, we get the total power. Now we all know that what is the relationship between RMS voltage and the peak voltage. So this A is the amplitude. What is amplitude? The peak voltage. Since I'm writing V here, you can write this A as VP also, where VP is the V peak value. Okay. Now, what is the relationship between RMS and the peak value? Your RMS voltage, say VRMS, okay, this is equal to V peak divided by √2. This is the relationship. And since we have VRMS square, so we substitute VRMS by VC by √2 and make it square. So your carrier power is equal to VC square by 2R. Now this VC is your peak voltage of the carrier. Okay. Similarly, we have two sidebands. You see how much is the amplitude of two sidebands? The amplitude of both the sideband, it is same. The amplitude of both the sideband components, that is equal to MVC by 2. Okay, and the amplitude of carrier component is VC. And from where did I come to these values? If you look at this expression again, see the amplitude of carrier is how much? VC. The amplitude of two sidebands, it is same, that is MVC by 2. So same thing I have used here. So amplitude of lower sideband and upper sideband is MVC by 2. Amplitude of carrier is VC. Okay. So that's why it is shown as PLSB equal to PUSB, which gives us sideband voltage square divided by R, which gives us the peak voltage divided by √2 divided by R, and this is what we get. So this is the sideband power in each of the sidebands, either lower sideband or upper sideband. So finally, what we want the total power. So we have to sum this carrier power and lower sideband power and upper sideband power. So if you do that, this is the final expression that you get. Okay. And if you take PC towards right hand side, then your total power in case of AM signal, okay, this total power is equal to PC into 1 plus M square by 2, where M is your modulation index of that AM. Okay, and PC we already know. What is PC? PC is your VC square by 2R. So this is the total power of the AM signal, which is equal to PC into 1 plus M square by 2. And you see here that if you increase the value of modulation index, then the total power in AM, it increases. Okay, means the more the level of modulation, the more is the power required for that AM signal. So I hope all of you have understood the concept of total power in amplitude modulated signal. Okay. So students, after we complete the relation of various components in AM signal, then let us have a look at two examples that will help us in further understanding of these power relations. So these are the two examples. These are very, very simple, just application of the formulas. So what we have, the peak carrier voltage is 150 volt. So peak carrier voltage, it means this is nothing but VC. Okay. Then this voltage is passed through a resistor, that is R, is equal to 100 ohm. Modulation index is given as 0.25. That is M is equal to 0.25, means 25% modulation is taking place. So you may be given a modulation index in terms of percentage. You could have been given here, say 25%. So in that case, you should have taken the value of modulation index is equal to 0.25. Fine. And we have to obtain the total power. Okay. And we know that total power is equal to the power in three components. So this is your carrier component. This is your lower sideband component. This is your upper sideband component. Okay. And formula we already know, VC square by 2R plus M square by 4 VC square by 2R. And if the value of VC we already know, value of M, R, everything we know. And if you calculate, you will get the answer direct. Okay, so this is how we obtain total power in the AM signal. Similarly, if we look at one more example, we have a 400 watt carrier. Okay, so it means the carrier power is given. We are given carrier power, that is PC. Okay, and it is modulated to a depth of 75%. Modulation depth means modulation percentage. It means the value of modulation index is how much? 0.75, as I told you in the upper slide. Okay, and now we need to calculate total power, and we know the formula of total power. It is equal to PC into 1 plus m square by 2. PC we already know. The value of m, it has been given as 0.75. You substitute all the values, you get the total power in the AMC. So these were some very simple examples to explain the concept of modulation index and the power contained in the AMC. Now let us move forward. So students, this is a very, very important concept. Now, if you look carefully at this figure, what is happening here? How many carriers are here? Obviously, there is one carrier signal. Okay, and in this figure, how many modulating signals are there? Okay, so obviously there is only one modulating signal whose amplitude is something, but I'm representing here as VC and VM as how many number of your carriers and number of your modulating signal. Okay, so now it may be possible that we have one carrier, but there are many modulating signals that I want to transmit from one user only. Okay, that means I want to transmit modulating signal 1, I want to transmit modulating signal 2, I want to transmit modulating signal 3, I want to transmit these three modulating signal, and I want to modulate a carrier using these three modulating signal. Okay, so obviously then the sum of these three modulating signal will be superimposed onto this carrier, isn't it? So the expression for the percentage of modulation that we have seen, that was simple expression dedicated to only one modulating signal, which was given as m equal to Vm by Vc. Okay, now what happens if I have more than one modulating signal? Okay, in fact, let me interpret this thing in a different way. It may confuse you that more than one modulating signal. Let me put it this way, that I have only one modulating signal, and in that one modulating signal, there are many sine waves. In fact, that is a more appropriate explanation for this slide, that I am modulating by several sine waves. Means I have only one modulating signal which consists of three sine waves, say S1, S2, and S3. Means only one modulating signal having three sine waves. In that case, how will I transmit those multiple sine waves through a same carrier? Okay, so it is a very simple thing. All that I need is I will calculate modulation index in a different way. So this formula I told you, this is for single sine wave. If I have more than one sine wave, then for each sine wave, I will obtain a different modulation index. For sine wave 1, my modulation index will be M1. That will give me M1 equal to Vm1 by Vc. And what will be my M2? M2 will be Vm2, okay, by Vc. What is Vm2? It is the amplitude of second sine wave divided by the carrier. Carrier amplitude will remain same because carrier is one only. Okay. So now what is this? This is M1. This is M2, V2 by Vc. M3 is V3 by Vc. Okay. And these individual modulation index, they will be squared, okay, added, and then root is taken. So this is nothing but RMS value. Root means square. So if I have to obtain modulation by several sine waves, then the modulation index will be obtained as root mean square of the individual modulation indices by your sine wave, individual sine waves. I hope this thing is clear to each and every one. This is very simple also. So we will obtain total modulation index in that case, which will be equal to RMS values of the individual, you can say, modulation by individual sine waves. Okay, and then we will use this total modulation index in our power relation. Okay, now this was the power relation that we had seen. So now instead of M, we will use MT, total modulation index, or you can say mean square modulation index. Okay, and see, this is what has been shown, PC into MT square. Okay, so if my signal, if my modulating signal has several sine waves, say M1 has several sine waves, S1 plus S2 plus S3 and so on, whatever be the number of these sine waves, I'll obtain the individual modulation indices. Okay, keep this as capital M so that it distinguishes between the modulation index. So this is my modulating signal M. Okay, so then I will obtain the total modulation index, that is MT, which will be obtained as root mean square. Okay, then for S1 I will have M1 square under root. For S2 we'll have M2 square. For S3 I'll have M3 square, and so on. Okay, and then this will be the total modulation index, which we will use for all the purpose. Fine. So this is how we obtain the modulation index when there is modulation by several sine waves. See, students, now you are able to clearly understand the mathematical formula here. But I want to bring one very important concept here. If you remember, I told you in the previous class that for the case of simplicity, I am taking my modulating signal as sinusoidal signal. But practically, my modulating signal will not be only sinusoidal. It will be some random signal. Okay. Then in case of random signal, or in case of not so simply mathematically definable signal, how will I be able to know the modulation index of my AM signal? So all of you have studied Fourier series and Fourier transform, and with the help of your Fourier series and Fourier transform, we can express our given signal. If say my signal is periodic, okay, then with the help of Fourier series, I can express my modulating signal as sum of various sinusoidal components. You already know that. Okay, say component S1, then component S2, then component S3, and so on, like this. Okay, let me take an example. Say if I have square wave, okay, it is a periodic square wave, and I want to obtain the modulation index that will be obtained when we amplitude modulate this modulating signal with the carrier. Then what will happen? What I'll do, I'll express this square wave as a sum of various sinusoids using Fourier series. Okay, and whatever sinusoidal components we have, from those sinusoidal components, I'll obtain different modulation indices, and then I'll obtain total modulation index, and I'll apply same thing. So any signal can be expressed as a summation of various sine wave components. So that is the main significance of this slide, where whatever specific example we have taken with regard to sinusoidal wave, that example can be generalized if you use this concept of modulation by several sine waves. Okay, I hope I am clear about this point. So this was modulation by several sine wave. Now let us move forward. So students, this is another important concept. In fact, general concept related to communication system. See, when any communication engineer wants to design any communication system, okay, we have certain resources in our hands, and those resources we want to utilize at its, in a best possible manner. So for any communication engineer, there are two most important resources which are, very, very important. One is power and another is bandwidth. Okay, see, let me give you one practical example. When we go to market to buy anything, what is the most important resource we have? The most important resource is money. If we do not have money, we cannot think of even going to market. Okay, so first we have first we keep money with us, and then we go for shopping in the market. Similarly, if you want to design any communication system, or if you want to, implement any communication system, we must have power and bandwidth in our pocket. So if we do not have power and bandwidth in our pocket, we cannot think of communication. So any communication engineer has to first buy or first attain power and bandwidth. Only then he or she can think of establishing any communication system. So now let us briefly talk about what is the meaning of power and what is the meaning of bandwidth. Power, you already know. In fact, we have obtained the power amount of power present in our amplitude modulated signal. Okay, this was the slide that told us the power present in the amplitude modulated signal. Okay, and we understand easily the concept of power, that power gives the signal the capability to travel. The more the power, the better it is. Okay, isn't it? Similarly, bandwidth. I talked about bandwidth briefly earlier. Bandwidth means range of frequencies. Okay, but to clarify the concept of bandwidth further, see, we all know that in any communication system, we have a transmitter and we have a receiver. Okay, and our signal is moving from transmitter to receiver. Fine. Now, it is the bandwidth that helps my signal to travel from transmitter to receiver. You can assume the bandwidth as a pipeline, as a simple pipe. Okay, that will help my signal to travel from transmitter to receiver. Say this is my transmitter side. Okay, and this is my receiver side. Okay, and this is my channel, which is behaving like a pipe. Okay, so the way we have water pipelines in our households or in our city, the larger the size of the pipe, the more the amount of water can flow through it. Okay, similarly, the larger the size of the pipe, or the larger the bandwidth available between transmitter and receiver, more the amount of signal that can travel from transmitter to receiver. So you can assume the bandwidth as a pipeline that helps our signal to travel from transmitter to receiver. Okay, so we want more power and we want obviously more bandwidth, because if my bandwidth is large, or if the size of the pipe is large, then more amount of signal can travel. Or if I have less amount of signal and the size pipe size is, you can say, large, obviously it will take less time to travel there. Okay, so I hope all of you have been able to correlate the concept of bandwidth with your practically available things. So obviously we need large power and large amount of bandwidth. Okay, and see, you must be reading in newspapers every now and then that you must have heard of the term spectrum, that before establishing any communication system, all these mobile communication companies, they buy spectrum. Buying spectrum means they are buying bandwidth. Okay, so if we have this much size pipe available between transmitter and receiver, or between two places, then what our government or regulatory bodies do, they divide this big pipe into small sized pipes. Okay, multiple pipes. Fine. And say this pipe is assigned to Airtel, this pipe is assigned to say Vodafone, this pipe is assigned to say Idea, from where you can send the signal. Okay, and the larger the size of pipe you buy, the more the amount of signal you can transfer through that pipe, the more the number of users that you can support. I hope now this thing is clear. And power here means the force. Power will give us the force through which our water or our signal will be able to transmit through a given sized pipe. Okay, so I hope with this thing you are clear. So obviously, if we have more power, if we have more bandwidth, obviously I'll be the most happy communication engineer. But as I told you, we have to buy bandwidth. So bandwidth comes at a premium. So we cannot have infinite bandwidth available with us. Similarly, power is also, it's not that we can introduce as much power as we can into the signal. We all know that all our devices are battery operated. Okay, we know the significance of battery power. Okay, we know how do we save our mobile battery power when it reaches at a critical level. How carefully we use our mobile in case less power is left in our mobile battery. Okay, so obviously we want to preserve power as well as bandwidth. Okay, for communication engineer, we have to optimally utilize both these resources, because both resources come at a premium. They are not free. Okay, and another important, very important point is there is a trade-off between power and bandwidth. For communication engineer, this is a very important thing. If a communication engineer wants to save power, if he wants to consume less power, then he needs more bandwidth. If he reduces power, then more bandwidth is required. If he increases power, then he can think of less bandwidth. So these power and bandwidth go in reverse direction. So that's why any communication engineer has to trade off between power and bandwidth. Okay, so whatever modulation scheme we will be studying, amplitude modulation we are studying, and other modulation techniques also that we will be studying, all those modulation technique, everywhere we will talk about the power requirement, we will talk about the bandwidth requirement. Okay, and if you take the example of amplitude modulation, we just talked about the power requirement of AM. Okay, now what we need to talk about, the bandwidth requirement. Okay, so for every modulation you have to keep this thing in mind, that power and bandwidth are the most important parameters. I hope everybody has understood this. Now let us move forward. So this is the slide which I showed you in the previous class as well. We had discussed frequency domain representation of AM signal. I just talked about bandwidth or spectrum. So that's why I have included this slide here for reinforcing your concept. So this is the time domain approach, and why we are discussing frequency domain approach, because we need to know the spectrum requirement, or we need to know the bandwidth requirement of AM signal. So this is the bandwidth requirement. Okay, so by looking at frequency domain representation, we are able to know that which frequency components are present and how much is the bandwidth required. Fine. So if you look at this figure carefully, the highest frequency which is available in AM is FC plus FM, and the lowest frequency is FC minus FM. and the bandwidth requirement is the difference between the two, and this is the bandwidth requirement, that is twice of FM. Fine. And in the previous slide, I told you that we want to save power, we want to save bandwidth. Okay. So obviously, whenever we, mathematically or graphically represent any modulation technique, we try to see the various ways through which we can save either power or bandwidth. And you will get an idea of it when we discuss about different forms of amplitude modulation. Fine. So I hope this frequency domain representation or the concept of spectrum or the bandwidth requirement is clear to you. That's why we have talked about the power relations in AM, and we have talked about the spectrum of AM signal. Next. Yes. So these are the various forms of amplitude modulation. We have talked about amplitude modulation in general. Okay. But this amplitude modulated signal, it will be available in different forms. We just talked about power and bandwidth. And now you will get that idea of power and bandwidth in this slide. Okay. We will generate various forms of AM, and we will try to save either power or bandwidth or both in some form. Okay. And as we try to save the power or as we try to save the bandwidth, it becomes a different form of amplitude modulation. Okay. Now the first form of amplitude modulation is double sideband full carrier. Okay. This is the original AM. This is the original AM, which you are observing or which we are discussing from day one. That is your double sideband full carrier, complete AM. Okay. And in short, we can see as represent it as DSB-FC, double sideband full carrier. Fine. Now, you look at this thing carefully. See, all of us are very, very selfish. Okay. So normally what we do when some person is of no use to us, we throw him or her away. Okay. So means like if our job is done, then we do not need that person. Okay. So in fact, a communication engineer is more selfish than a general human being. If he doesn't, need anything, then that thing becomes useless. And same thing is happening with carrier. Okay. What carrier is doing? Your carrier is, making your signal reach from one place to another place. Okay. And how did we obtain AM? When we obtained AM, we got three components. Okay. One component was VC, that is carrier component, this one. Once we obtained AM, we got three things, if you remember. We obtained carrier, we obtained lower sideband, we obtained upper sideband. Okay. Now, because of modulation, before modulation, what was the case? We had two frequencies. One was FM and another was FC. These two frequencies were available with us before modulation. After modulation, what we had three frequencies. FC, okay, then FC plus FM. This concept is very important. Please look at this concept very carefully. And the third frequency that we have obtained after modulation is FC minus. Okay, so these are the two frequencies before modulation. Before. Okay, and these are the frequencies that we have obtained after modulation. Fine. Understood this point? See, because of modulation only, we have obtained a frequency FC plus FM. Fine, which is more than FC. It is more than FC. Okay, and FC minus FM is also a high frequency. Okay, so once we have got two higher frequencies, okay, then what's the need of FC? Okay, so basically what I want to say here, if we have a transmitter, okay, then see, this thing is happening at transmitter only. It doesn't mean that I'm now removing carrier fully. Say we have a transmitter and a receiver. At the input of transmitter, I had two frequencies. One was FM and another was FC. Okay. Now, what transmitter does? It combines the two, and here, okay, at the output of transmitter, due to modulation, in fact, due to modulator, we get three frequencies. One is FC, another is FC plus FM, and third is FC minus F. If you remember, the main logic of using carrier was that carrier was a high frequency component which could travel for a longer distance. Okay, and that's why we needed carrier. Now, because of modulation, we have got three components: FC, FC plus FM, FC minus F. FC plus FM and FC minus FM both are high frequency components. Okay, so then we may think of removing the carrier here, carrier frequency here, and we may transmit these two only. These two may only be transmitted through the channel. We cannot do away. We can do away with the this FC. Do not say that FC is carrier. You can say that carrier frequency we have removed, because we have used carrier to obtain FC plus FM and FC minus FM. Now we do not need carrier. We have become selfish. Okay. So what we do, we can think of removing carrier before transmitting. Okay. We can think of removing this carrier because we do not need this carrier. So we can transmit only the two sidebands, lower sideband and upper sideband, that is FC plus FM and FC minus FM, and we call that as double sideband suppressed carrier. So if in the double sideband full carrier, you filter out carrier frequency, okay, we are left with only two sidebands. Fine. It becomes double sideband suppressed carrier, double sideband SC, DSB, SC. So this is another form of amplitude modulation that we have obtained. Now the question arises that what advantage we have got by removing FC or by throwing away carrier, because if we send USB and LSB, our bandwidth requirement is same, because our highest frequency and lowest frequency that doesn't change because we have removed the carrier which was in between. So bandwidth requirement remains same. But dear students, by removing carrier, we are able to save power. So if you see in this expression that if you see in the total power, how much is the total power? Total power was PT equal to PC plus, I'm opening that expression, it was PC into M square by 2. And what was M? M was modulation index. Okay, so total power is equal to carrier power, and this was your sideband powers. Okay, and if you analyze this carefully, the total power which is present in the carrier component is 67%, approximately 67%, and the total power which is present in these two sidebands, it is just 33%. So if after using carrier, we have got two frequencies which are higher frequencies, and our information signal is present in those sidebands only. In the carrier FC, we do not have anything, and we have to become very selfish. Obviously, we have used carrier to obtain these two frequencies, but now since carrier is consuming 67% of the total power, why do we go with that carrier? We will think of removing the carrier, and if we remove carrier, our 67% power requirement will be saved. Okay, that's why in order to save power, we think of removing the carrier. Okay, and that's why your last slide was very, very important. where I told you that power and bandwidth are the two most important resources. So here in double sideband suppressed carrier, we are saving power, not the bandwidth. I hope this point is clear to each and every one. Okay. So students, we talked about the second form of amplitude modulation, and that second form is double sideband suppressed carrier. And I told you that we are thinking of removing the carrier, and the main logic behind that is because 67% of the power is present in the carrier part, and we have already obtained the modulation sidebands. So that's why we can think of removing the carrier, and we remove the carrier, and by removing carrier, we are able to save the power. Now, one last important point related to double sideband suppressed carrier is, I thought some of you will ask a question related to that. But anyway, you need to notice one point that I'm not saying double sideband without carrier. I'm saying here double sideband suppressed carrier. Okay. So what is the basically meaning of this suppressed carrier that we need to understand? The meaning of suppressed carrier, in fact, the English meaning of suppressed means which is something which is, you know, reduced in its energy or in its amplitude. Okay. So this is not without carrier, this is suppressed carrier. You need to look into the word suppressed. Okay. So just to, you know, to your pleasure, I'm not removing the carrier fully. The doubt that you people had that without carrier, how will our signal travel? Though I answered that question, but I'm not fully removing the carrier. I am using suppressed carrier. Suppressed carrier means I'll not totally remove the carrier. I will send a small amplitude carrier. I will reduce the amplitude of the carrier component. Okay, say this much, and this part I will, you know, suppress. Okay, so if I reduce the amplitude of the carrier, in other words, if I suppress the carrier, okay, maybe I'll not be able to save entire 67% of the power, but say for example, if I am able to save 50% power, I keep some amount of carrier in the signal, okay, and instead of sending full carrier, I send suppressed carrier. Okay, and what is the logic behind keeping a small amount of carrier? The logic is that if I remove carrier 100%, then there will be synchronization problem. Okay, because you know that we need to transmit our signal from transmitter to receiver. Okay, so if we remove the carrier fully, if you remove the carrier fully, then you will not be able to obtain good synchronization, complete synchronization at the receiver side, because we will require some carrier reference at the receiver side. So that's why for synchronization purpose, we do not fully remove the carrier from the transmitter side. We send suppressed carrier instead of zero carrier. Okay, and this suppressed carrier will act as a reference point that will help us in regenerating the carrier at the receiver side, and that regeneration of carrier at the receiver side is required to demodulate the signal. Okay, so I hope this point is clear. So I have clarified the concept of double sideband full carrier. I have also clarified the concept of double sideband suppressed carrier. We have also discussed why suppressed carrier is required. We have also discussed that what advantage do we get if we suppress the carrier in your amplitude modulation. Okay, so students, I stop here and we will continue in the next class.